The engineering behind helicopters is surprisingly complicated. Seriously, that's what an aeronautical engineer who studied the theory in depth is telling you. It's a complex topic that people often underestimate, but you know why we're here on this channel. In this video, we'll discuss helicopters again, the second video in this series that I'm making so you can fully understand the physics that govern helicopters. How do key helicopter systems operate, and why do helicopters have unusual designs? And that's why in this video, we're gonna go over the main systems of helicopters that ensure they work properly. Actually, what I'm gonna tell you is a summary of the helicopter course I took in the Masters in Aeronautical Engineering. So, if you really want to understand how helicopters work, trust me, you've come to the right place. Let's get to it. The first thing is that helicopters, just like airplanes, have to be able to rotate on all three axes. That means they have to be able to perform yaw, pitch, and roll movements. From my point of view, the easiest one to explain here is yaw, since as I explained to you in the previous video of the series, helicopters have a tail rotor because when the engine spins the main rotor of the helicopter, by Newton's third law, the rotor will make the engine spin in the opposite direction. Therefore, if there were no tail rotor, the helicopter would spin like a top. Can you control the force it makes? So if it doesn't make much force, you're going to let the helicopter spin a little. If you use too much force to keep the helicopter straight, you'll spin the other way. And now, let's talk about pitch and roll movements, which are actually generated the same way in the helicopter. Let's see, if we wanted the nose of the helicopter, for example, to go up, what we would have to do is adjust the rotor of our helicopter. At the front part of the rotor, every time a blade passes through the front of the rotor, it will increase its angle of attack so that more lift is generated in that area of the rotor. And therefore, a movement would be generated to raise the nose of the helicopter. We can use this theory if instead of wanting to raise the nose of the helicopter, we want to turn the helicopter, right? Is it exactly the same? But of course, can we do this? Can we make it so that every time a blade passes through a certain part of the rotation, the angle of attack changes? Yes, it's possible because of the swash plate, though it's hard to explain how it works in words. But I'm very lucky to have some amazing footage since I was invited to visit the CITE facilities, which is a technical training center for aeronautics and helicopters and airplanes. It was amazing. They let me try anything I wanted so you can see the helicopter's swash plate. It's a part that's in the rotor, which allows a certain part of the rotor to rise in such a way that it's anchored to the blades and changes the angle of attack of the blades, but only in one area of the rotor. That's how helicopters move. If, for example, we have a stationary helicopter and we want it to move backward, what we have to do is increase the angle of attack of the blades. Therefore, more lift is generated at the front. The nose of the helicopter will rotate upward, and when this happens, the rotor disc will tilt a bit. And that will make the lift force generated by the rotor no longer point only upward, but also have a small contribution backward. And that's the reason why the helicopter moves. So yes, helicopters can move because of this small angle given to the rotor disc. And for those of you who are wondering, how does a helicopter ascend or descend? Well, actually, helicopters are configured. They are set up before the flight, or at least generally speaking. This ensures the blades spin at a constant speed. The speed stays the same. Only the blade's angle of attack, known as the collective, changes. For example, in the videos where you can see me inside the helicopter, it's my left hand with my left hand. If I were to raise that lever, the angle of attack of all the blades would increase equally, okay? The key is that it increases all the blades equally, but the cyclic, this one in front of me, right? If I push forward, what it will do in the end is increase the angle of attack of the blades at the rear part of the disc, in such a way that when the blades pass through there, they generate more lift and tilt the rotor disc. And then, the pedals are for the tail rotor. The pedals are what give you the ability to yaw. Here we can already begin the first very interesting engineering analysis. Even if you knew before, I'm sure you didn't know this. It's said that airplanes are fixed-wing aircraft and helicopters are rotary-wing or moving-wing aircraft. Do you know what the main difference is? I would say that's really the main difference between a helicopter and an airplane. Besides the fact that, of course, in a helicopter the blades are rotating and in an airplane they're not. Well, in an airplane, the thrust system and the lift system are completely decoupled. The engine gives you the thrust and the wings give you the lift. In a helicopter, the rotor gives you both things. It gives you lift and it gives you thrust. Tilting the disc slightly generates a small force that enables the helicopter to move. So actually, helicopters that move at high speeds, 300 kilometers per hour, over 200, 400, sometimes even 500 kilometers per hour, which is crazy. Well, they achieve that speed just by tilting the rotor disc a little. Honestly, I find it fascinating because the air resistance force is actually very small. And here, in addition, we can add something else as well. And if a helicopter is hovering, it's not moving up, down, or sideways. It's just staying still. Well, if we suddenly rotated the rotor so that it moves forward, so that the helicopter moves forward, well, because the lift force suddenly tilts to one side, the lift force that goes upward, meaning the vertical component, decreases a bit. So in reality and in practice, this can be seen. If we have a helicopter hovering and it suddenly tilts forward, it's going to drop a bit, it will go a little downward and forward. Then, well, it can recover. Or if the pilot has a lot of experience, he can compensate for that by giving a bit of collective. But the best part is still coming. I'm going to explain to you the different types of tail rotors that a helicopter can have, and I'm going to explain how they work and why you would use one or another. And also at the end, I'm going to tell you what the advantages and disadvantages of the different types of tail rotors are. The first one is the classic one, the traditional tail rotor. I won't discuss it now since you likely know all about it. We'll talk about its pros and cons later. Then we have the fenestron, which actually looks the same as the traditional tail rotor. It obviously has the same functionality, but it's not the same. But there are some advantages we'll discuss later, but for now, let's focus on the no-tail rotor, which is truly fascinating. It stands for no-tail rotor, so you can picture it. Let's see how it works. In this system, the helicopter has a small fan inside, meaning a small ventilator that directs air through the tail and out through a small opening. However, most people don't know that air exits along the whole tail. It doesn't simply exit straight out to one side. No. It comes out along the entire tail through some small holes. And what this does is that the air that's already going down because of the main rotor, since the main rotor is deflecting the air downward, well, the air comes out through these small holes. What it does is that the boundary layer of air being deflected downward from the rotor stays attached to the tail for a longer time, so it's going to be deflected to one side, and this cancels out the torque generated by the main rotor. Of course, this happens along the entire tail boom, the purpose of the air coming out through the holes along the whole cylinder. It's exactly the same as when we try to re-energize the boundary layer on an airfoil on the upper side. For example, as I mentioned in this video, which I recommend watching, I discuss slats, flaps, and related topics. There you have the slats. You could clearly see that their function was to let high energy air enter the upper part of the airfoil, and what it did was prevent the airflow from separating, keeping it attached to the upper surface of the airfoil for a longer time. Well, here it's exactly the same. The air separating downward remains attached to the tail cylinder longer and then exits on one side. So it's like a kind of Coanda effect is created, of course, intentionally, so that the air is released to one side and a counter torque is generated to cancel out the torque from the main rotor. As I was saying, it's true that at the end of the tail you have a hole, a large opening where the air also comes out. That opening is what gives you variable control, the one that lets you change the direction in which you want the air to come out, to give more or less counter torque as in case you want to make a yaw movement or whatever. Honestly, it's crazy. I was the first one to misunderstand how the no-tail rotor works from the very beginning, but once I understood it, it's amazing. It's incredible. So of course, now let's see what the real advantages and disadvantages of these systems are and why they're used. Or why a different one is used in some designs. Let's begin with the first, the standard tail rotor with no protection. If it's the one that's used the most, the one that's been used the most, is it because it's the best, or just because it's the one that's been used the most because it's the simplest? You just put a rotor there and forget about it. But of course, this obviously has several problems. The first one is that it's unprotected. You could have a crash landing, because imagine a landing where the helicopter hits with the tail, lands on the tail, you break the rotor, and repairing that is crazy. Second problem, when that's spinning at high speed before the helicopter is about to take off, or after it has landed, it's super dangerous. You can't see it spinning, and unless you know there's a fast spinning tail rotor, you won't notice it. And it wouldn't be the first time someone walks by there and loses a hand, or even worse. So that's the second problem, which is actually quite serious. The third problem is, of course, the noise. The noise generated by this rotor is much greater than the noise that can be produced. For example, in a fenestron, because it's covered. Mainly, those are its three main disadvantages, and the fenestron turns the tail rotor's weaknesses into strengths. Because since it's enclosed, if the helicopter lands and hits the tail, you're not going to damage the tail section, but you also won't damage the rotor. I mean later. It's very unlikely anyone would get hurt by the fenestron. If you lose a hand, it's only because you actually put your hand inside. So it's not like the tail rotor that's just out there and is actually quite dangerous. Also, since it's enclosed, the noise is greatly reduced. Whether it's simply because the vibrations are reduced, since you have many more supports for the rotor, just because of that, the vibrations are reduced, and in the end, the noise is also reduced. Speaking about the Rotor, its main advantage is that it's not dangerous at all. I mean, when the helicopter is operating, you can go and grab onto or even hug the tail if you want, and nothing will happen to you. But, on the other hand, it's a bit worse in terms of maneuverability. And also, here the anti-torque system and the rotor system are attached. As I mentioned, it works by the rotor deflecting air downward, which then spins in the cylinder and gets deflected to one side. You're already combining two systems that are very closely related, which usually isn't a good idea. And on the other hand, we have something new that Bell, the company Bell, has introduced, which is actually a few rotors, actually 4 electric rotors, used as an anti-torque system. They claim it's very interesting because since everything is electric, all the systems that go to the tail are electric. Well, you can have 3 or even 4 cables that serve the same function, since they don't weigh much, so you can actually have a lot of redundancy. If one electrical system fails, there's a backup, and if that fails, there's another. Actually, it's easier here to implement fly-by-wire, which is basically the idea that you tell the aircraft's computer how you want to fly the aircraft, and the computer will do whatever it needs to do so that the aircraft moves the way you want. Here, of course, since it's controlled by an electrical system, this is much simpler, but of course it has many detractors, the typical people who really like it. Well, like how airplanes or helicopters used to be and all that, so they're definitely going to be against this. The truth is that there isn't much information about this, since they just came up with the idea a few months ago. And actually, well, the patent came out in 2019, I think, even at the end of 2019, so this idea is really new, okay? Now we'll answer the last video's question and introduce the next question for the following video. In the last video, I asked why drones lack an anti-torque system or a tail rotor. The first person who gave me the answer was... Here we have it, okay? And indeed, they don't have an anti-torque system. Because simply by having 4 propellers, 2 spin in one direction and 2 spin in the other. Diagonal ones spin one way, the other diagonals spin the opposite. That's it, science junkie. I hope you really enjoyed this video. I think I've been able to illustrate here pretty well everything I've learned in my helicopter course, and, well, generally quite a lot about helicopters. And now let's go with the question for the next video, but first, leave me a big like and subscribe. Of course, if you haven't already. Among these 3 helicopters, tell me which one you think is the fastest. Of course, also tell me why. We'll see. In the next video, we'll talk about strange helicopters, because they have designs like, for example, this one or this one. That's it, Science Junkie. Hope you liked it. See you next time on the Science Blog.